Hello everyone, this is Sir Aris. Let us discuss about, so this is the last part of chapter 3, non-homogeneous equations and method of undetermined coefficients. Non-homogeneous equation can be written in this form where you have the usual second order differential equation here, but the left side is not zero, so there's a function with respect to t. P, oops, P, Q, and uh, G are given functions of in on the interval I. The equation, if we set this to zero, is called the homogeneous equation corresponding to this non-homogeneous equation. Now let's consider this theorem. If y1 and y2 are two solutions of the non-homogeneous equation, or non-homogeneous equation, then their difference y1 minus y2 is a solution of the corresponding homogeneous equation, this equation. If y1 and y2 are fundamental sets of the homogeneous equation, then we can write y1 minus y2 equals c1 y1t plus c2 y2t, where c1 and c2 are certain constants. To prove this, what um, what we need is that, so we know that y1 and y2 satisfy the equations L y1 t equals g t and L y2, so that's y g t. Subtracting the two, you have L y1 t minus L y2 t equals gt minus gt. So this minus this, so that is just equal to 0. For linear operators, this is a little bit technical, but L here, which is our short-term notation for this expression, it is technically called a linear operator. So L uh, y1 minus L y2 is equal to L y1 minus y2. So uh, Ly1 minus y2 is equal to 0. And that's what we need to prove that y1 minus y2 uh, is equal to this sum of the fundamental set of solutions. Now let's consider the general solution of the non-homogeneous equation of this theorem. Uh, we can write the general solution as this, where y1 and y2 are fundamental set of solutions of the homogeneous equation. C1 and C2 are arbitrary constants. Y is a specific solution of the non-homogeneous equation 3.1. So given a particular or a specific solution plus the fundamental a linear combination of the fundamental set of solutions, that gives us the general solution. To prove this, um, we use theorem 3.5.1, so the first one here. Using this theorem, we have y1 minus y2 equals c1 y1 plus c2 y2. What we do, we just set y1 to phi and y2 to y. In this case, you have this phi minus y equals this, so we write phi t equals c1y1 plus c2y2 plus um, yt. That's our general solution. So what we want to do next is to find the particular solution y. One way to do it is to use the method of undetermined coefficients. To find this specific or particular solution, we use the method of undetermined coefficients, where we follow these steps. First is we make assumptions about the form of the particular solution. Second, we substitute this into the non-homogeneous equation and determine the coefficients. If we are successful, then uh, that's enough. We end there in step 2. But if not, we have to modify the initial assumption. The advantage of this method is that it's straightforward to use. So we just have to make assumptions again and then find the coefficients. However, it is we are limited to use it only for familiar equations because the first step is to make assumptions. We have to be familiar on. We have to um, we have to know in advance what would be the possible forms of the particular solution. And for more difficult problems, that would be uh, very difficult, if not impossible, to find. So let's do an example. Find a particular solution of y double prime minus 3y prime minus 4y equals 3e to t. The, the form of the particular solution, we can try some multiple of e to t. So say our particular solution is equal to um, coefficient a times e to the power of 2t. So if we take the first derivative, that would be 2a e to t. Second derivative, oops, y. Second derivative is 4a e to t. And then we substitute this to equation 3.5 here. So we have y double prime is 4ae to t right here. Minus 3 y prime is this. It's 2a e to t. Minus 4 this 4a to t. This and this cancels. You have minus 6 and 3. So what we have is that this minus 3 times 2, which is 6a, should be equal to 3. So minus 6a should be equal to 3, which tells us that a should be equal to minus 1 half. Or our particular solution should be minus 1 half e to the power of 2t. Okay, another example, find the particular solution of this. So similar to what we did, let's try um, y t. Oops, let me write that properly. Y t multiple of sine t, say a sine t, so that y prime is a cosine t and y double prime is a or negative a sine t. And then we substitute this equation 3.6. You have y double prime is minus a sine t minus 3a cosine t is here minus 4a sine t equals 2 sine t. So what we have is minus a and minus 4a, that becomes minus 5a. We also add this minus 2 minus 3a. Now what, for some values of t we can find a solution for a, but there is no no solution for a that works for all t. Hence, we need to find a different form for our particular solution yt. Let us try y equals a sine of t, but aside from that, let's add it with b cosine t, and we'll find for a and b. If you take first derivative, that would be a cosine t minus b sine of t. Second derivative, that's minus a sine t minus b cosine of t. And then we substitute. So when we substitute, we have minus a so this is y double prime minus 3y prime minus 4y equals 2 sine t. So you have a sine t minus b cosine t, okay, minus 3y prime. Y prime is a cosine t minus b sine t, okay, minus 4y. So let me write it here. Minus 4y is a sine t plus b cosine t equals 2 sine t. Now let's group terms here on the left side containing sine t. Let's say minus a sine t plus 3b sine t. What else? Minus 4a sine t. There's also this 2 here, but we'll keep it in the right side. Plus, we have here minus b for all with cosine t. You have 3a minus 4b cosine. This is cosine t sine t. So here this one becomes minus 5a plus 3b sine t plus negative 3a minus 5b. So 3a plus 5b equals 2 sine t. So we have two equations, minus 5a plus 3b equals, so this sign here and this are the same, so that's 2, and minus 3a minus 5b equals 0. So they have two equations, 1 and 2, which we need to solve simultaneously. Okay. What you can do, you can set, so from 2 you have um, 3a equals negative 5b, or a or b, or let's use b equals negative 3 over 5a, and then substitute to 1, you have minus 5a plus negative plus 3 negative 3 over 5a equals 2. If you multiply both sides by 5, that would give, this would be minus 25a minus 9a equals 10. If you want to simplify this, you'll get a equals 10 divided by 34, or that's 5 over 17. You use that, you go back here, so this means that the b here equals negative 3 divided by 17. Therefore, y is equal to minus 5 over 17 sine of t plus 3 over 17. Oh no, there's a minus here. You have the minus here, this becomes plus. Okay, 3 over 17 cosine of t. Okay. There are also, let's talk about other possibilities. Say if the non-homogeneous term is a polynomial, we assume yt is a polynomial of the same degree. If you have g, which can be written as a combination of different functions, and if it is easy to find individual particular solutions corresponding to equations where the non-homogeneous term are one of these uh, terms in the sum, say y1 is the solution for this, where the homogeneous term is, or the non-homogeneous term is g1, y2 is when the non-homogeneous term is g2, and so on, then the sum y1, capital letter y1 plus y2 and so on, is a solution. So this is solution of the equation where the non-homogeneous term is g. Um, if there is any duplication in the assumed form of y with the solutions of the homogeneous, so the homogeneous term is when this is 0. So if you know the solution of the homogeneous term, and let's say one of those are similar, or uh, a duplicate of an assumed form of yt, you can try to multiply y, or the assumed form, by t, or if necessary by t squared. And that's it.